Okay, now we are recording the session. Yeah, Sugam, we can start today's session now.
Okay, thank you. So as we discussed yesterday that we will make a one WhatsApp group, and that already has been made, and I think everybody has joined. From today onward, I will start sharing my lecture notes also. And here, this group has been made to discuss the questions or any doubts which arise now during the, not during the lecture, but even after the lecture also. So let's make this group more productive and start sharing our questions and doubts. So now I think just I can start. On the So I'm audible to all of you, I hope so.
Yes, sir, you are.
Okay.
You are audible.
Yes, and video is gone, right?
Yeah, video is gone. And yeah, if you start typing, I think
Okay.
it should
I,
also
I
work.
think just to avoid the interruption, I can uh, stop my video. So today we will be discussing about the quantum mechanics fundamental. And as we discussed that we will focus mostly on those sections which are required to understand the quantum computing part. So just to make your interest and uh, bring a flow in our topics, I will give a little bit brief history how the quantum mechanics started. I mean, if you look at before 1900, I mean, I can say a classical physics era. Everything was fine. People were very happy. The major theory developed before this was the classical physics, or you can say Newtonian mechanics, particularly the Newton mechanics. And you know that this theory or this mechanics determines the law of motions. Particle follow well-defined trajectory under forces, and this is completely developed by the Newton mechanics. So all the objects are moving, their dynamics was discussed in the Newton mechanics. Then we have the electromagnetic theory. And this tells you about the all electricity, magnetism, and the light also. Then we also had thermodynamics. And statistical mechanics. So these laws governs the energy, heat, entropy, and thermodynamic properties of cluster of atoms or molecules, and waves and optics. So everything was well done. And even the scientists or researchers, they were in the view that we have understood how nature works. But then few experiments and their outcome, they created the crisis at that time. So crisis arises because of certain experiments, and those experiments includes like black body, spectrum. The second was the photoelectric effect. Third was the atomic spectra, atomic spectrum. So these experimental outcome of these experiments were not understood or not explained with the existing classical theory. Neither these theory were able to explain the black body spectrum, nor the photoelectric effect, nor the atomic spectrum. So it was obvious that at that time, this created a chaos in the scientific society, and the people started thinking how to explain. And particularly here, what I can do, we can simply focus on the one experiment that is called the black body radiation spectrum. And quickly we can go through it and see how this led to the development of the quantum mechanics. So when you talk about a black body spectrum, I mean, if there is any black body, so black body is the object or a body whose surface absorb every radiations irrespective of the frequency. So it is a perfect absorber and perfect emitter. So if you take a black body and you hit it, then it is going to produce radiations. And if you measure this radiation, spectral density of this emitted radiation as a function of frequency at a different temperatures. So this is a well-known spectra of black body radiation at a certain temperature T, maybe let us say 1800 Kelvin. And if you try to see the spectrum at lower temperature, then it is how it's going to look like. Maybe this can be, let us say, 1000 Kelvin. So you see that this is how the black body radiation spectrum looks like. And at during this time, as I mentioned, that people were trying to understand that how this spectrum is produced. Many scientists, many researchers, they try to find a theoretical formula that can fit to this experimental graph. Majority of them failed. One very sincere effort was made by Rayleigh and Jeans. And they said that they took one black box cavity of a rectangular shape. And they said that when the atoms, charged particles, may be atoms or electrons, when they are oscillating, so they emit radiation. So this cavity is going to filled with the radiation. And as a result, inside the cavity, you can going to have a standing waves. What Rayleigh and Jeans, they said that there are standing waves are going to form inside. And they said that we can calculate the density of the radiation. And they said that this is possible if you calculate the density of the standing modes and average energy per standing modes. And finding the standing number of standing waves density is easy. The small mathematics, you can do it. I will also give you as a homework. This is how is the first part. And to calculate the average energy per standing per mode, they took an assumption The assumption they took is that when these atoms or electrons, when they are oscillating, they're going to emit radiation. So the energy they're going to emit into the cavity is filled with the radiation. So the exchange of energy, or I can say, they said that any amount of energy can be exchanged. So any amount of energy can be exchanged between matter and radiation. So they said this matter means atom or molecules, electrons, charged particles, when they're oscillating, they can emit any radiation of any energy. Similarly, this radiation inside, they can take this energy, and they can also, when they're going to hit the surface of the wall, then any amount of energy can be transferred from the radiation to um, uh, the wall. And based upon this, they used the Maxwell-Boltzmann distribution and calculated this average energy. And they found that this is equal to KBT, and this is a famous equipartition theorem. You can just go through this in detail, and then you can see that you can put the value here, and this is what is the expression the Rayleigh engines they got. And if you now try to plot this UV as a function of frequency, then you see that this graph is going to increase in a parabolic sense and going to become infinite at higher frequency. So this is the graph from the Rayleigh genes, and you can, they says that key at very higher frequencies, the density of the radiation become infinite. I mean, we should give a credit to this Rayleigh engines, because this equation correctly predict the radiation intensity at lower frequency. You can see that at lower frequency, this is completely not fitting the experimental graph. But only at a higher frequency, this is going to diverge and going to become infinite. And technically, at what I can say that at a very high frequency, we can say that this object, this black body object, this going to emit infinite energy. So at higher frequency, this black body object going to emit infinite energy. And this frequency is not, but generally in the ultraviolet region. So technically, this says that this black body in the ultraviolet regime, this going to emit infinite amount of energy. And this result is non-physical, because this is not true. And this is what is known as a ultraviolet catastrophe. So this way you can see that the Rayleigh Jeans law, this is also called the classical model, to explain the black body spectrum, failed to explain the or find a expression which can fit the experimental curve. Now, in this effort, another revolutionary breakthrough was made by the Max Planck in 1900. In fact, if you go to the history, you will find that this ultraviolet catastrophe, okay, created one kind of crisis again in the scientific society. So Max Planck, he tried to find a formula or mathematical formula that can fit this curve. And in this research, he made a revolutionary assumption. So he said that the exchange of energy in the matter and the radiation is not continuous. He said that the exchange of energy between matter and radiation is discrete. And he said this is equal to E n time h nu, where this n can take any value from. So he said that when you talk about matter, so when the particle is oscillating, so it can emit radiation. So it can emit radiation either of energy h nu, or it can emit radiation of energy, let us say 2 h nu or 3 h nu. So that is the assumption he made. And accordingly, when in this black body, inside the black body, the radiation is filled with this particular energy, and these radiations, when they're going to hit the again this metal surface or material surface, again they can transfer energy to the matter. Okay, only either h nu or 2 h nu or 3 h nu. So this is the assumption was taken by the Max Planck. He said that the exchange of energy is not continuous but discrete, and this is equal to nh nu. And based upon that, and he said that the system, of course, the parabolic here, and this energy, you can mark this energy, that is h nu, and then 2 h nu and 3 h nu. And he said that key by using this now Maxwell-Boltzmann distribution, again, one can calculate the average energy here also. Now, considering the discrete energy, what he found that this average energy is h nu upon e power h nu upon kBt minus 1. This is different from the classical. Look at, in the classical, energy is independent of frequency, average energy. But when you consider that exchange of energy is not continuous but discrete, then the average energy depends upon the frequency. And from there, you can see this U nu becomes then 8 pi nu square and c cube, and into this quantity h nu upon e power h nu and kBt minus 1. And this graph, now when you're going to plot, so if I look at here, U nu and nu, this is the experimental graph. And here is the, I mean, if you take the, I mean, while fitting the graph, he took the value of h equal to 6.625 10 to the power minus 34 joules second. And by taking this value, okay, when you fit the graph, this graph completely superimpose on the experimental graph. So the long-term crisis was resolved by the Max Planck. And even the Max Planck was not convinced with his assumption when, I mean, see, it is very natural to think that when the matter is producing a radiation, so it will produce radiation in the continuous manner. It's natural to think like this. It is unnatural to think that this matter is going to emit radiation of energy h nu or like 2 h nu or 3 h nu. It's much natural to assume it will produce all sorts of energy in a continuous range. So in that sense, Max Planck was not it's himself convinced with his theory. And he sometime even said that it seems like he has made some mathematical trick, which is giving the good result, but something much deeper understanding required. But mathematically, this was giving a correct result. But this has led to the another very important concept in the radiation. Before Max Planck, you think about the radiation was behaving like a wave only. And there were many experiments to prove it. For example, interference, diffraction, etc. So there were experiments which proves that radiation or EM waves, okay, they behave like waves. But after this Max Planck, okay, so Max Planck said that this radiation is discrete. This is in the form of packets. So they are actually acting like particles. So after this Max Planck, these EM radiations, they start behaving like particles. So this has led to a dual nature of radiation. At that time, there was no experiments to support the particle nature of the radiation, but later on, uh, interpretation of photoelectric effect by Einstein, okay, supported particle nature. So even the photoelectric effect, if you look back, I said that there were many experiments like black body and even photoelectric effect. So photoelectric effect was not, outcome of the photoelectric effect was not explained with the existing classical theory. And then Einstein, when he was very much inspired by the Max Planck concept of the quantization, so by taking the quantization condition of radiation, he explained each and every outcome of the photoelectric effect. And after this, then it was formally established that the radiations has a dual nature. So there are many outcome of the photoelectric effect, like why the photons are emitted only, no? Only, for example, when there is a radiation incident, then you know that the photons energy frequency is more than nu naught, then only the electrons will be emitted. Okay, this is the first outcome. Then the second outcome, like this ejection of electron is instantaneous. There's no time lag. Is a completely instantaneous. Okay, and the kinetic energy doesn't depend on the intensity, it depends only upon the frequency. So these outcomes were not explained with the help of the classical theory, but by considering E equal to NH nu, okay, so this was completely explained. So this interpretation of the photoelectric effect by the Einstein supports the particle nature of the radiation. So after this, the particle nature was completely established. So it was accepted by all the scientific community. Yes, the radiations have a dual nature. They behave like a wave also, and they behave like a particle also. Okay, so let's take a break here, and break means let's take question from your side. So any question up till here, anybody want to ask?
Yes, sir, I have a question.
Yes.
Yeah. Sir, you told that according to Max Planck, the exchange of energy and matter between radiation is not discrete, it was continuous. And over there, you wrote E is equal to NH mu, where N can take even zero value.
I said that this is not continuous, but discrete. Okay.
Yeah, sorry, discrete, yeah.
Yes. So
But
N0 means no energy exchange. Okay. He said that n is a integer number which can take value 0, 1, 2. Of course, the energy exists only when n equal to 1.
means N equal to zero is not valid, or maybe it's not observable, is it so?
No, I mean, n0 means no energy in this. So he said that the energy is going to be discrete in nature, simply. Okay. So the value start from 1, 2, 3 only. Technically, I mean, n0 doesn't correspond to any energy, a zero energy.
Thank you.
In fact, I can tell you there was an interesting story. The Max Planck, when you talk about N0, actually, although we are here not showing this part, but Max Planck was the first person. Actually, he proposed the idea that there is a 0 point energy which correspond to n equal to 0. So, but anyway, we will divert from our topic now. So, but he was the first person in the scientific history to propose that a vacuum is not a vacuum, but inside the vacuum there is energy, and this energy is correspond to something that is called the 0 point energy, and its value later was calculated. Anybody else? Okay, so if not, then
Sir,
yes.
this 0 point energy was calculated later.
Yes.
Can you tell me
Yep.
when?
It was calculated properly when the Schrodinger equation come into picture and when they solve the harmonic oscillator problem.
Okay, fine.
So, so now we have this dual nature of radiation, and after that, and this led to the birth of the quantum mechanics. Now you can see, but actual quantum mechanics start after the de Broglie. So de Broglie, he was very much inspired again by this dual nature of radiation, and he proposed that why only radiation has this special feature of having a dual nature. It's behaving like a wave also and particle also. He said that why not matter, which in natural form behave like a particle, but why it cannot behave like a wave. So he proposed this hypothesis that the matter also going to behave like a wave, okay? And then he proposed the idea of a de Broglie wavelength. So if matter has a certain, matter means having a non-zero mass, non-zero rest mass. So if you have a particle like electron or proton or neutron, which having a non-zero rest mass and some velocity, and if you know the mass and velocity, you can tell that what will be the wavelength of this wave, okay? And later on, this wave is what is called as the matter wave. And the whole quantum mechanics developed around this matter wave. But after this, even there was no experiment evidence to prove that matter is really behaving like a wave. I mean, electrons behaving like a wave. There was no experimental proof. And later, their experimental proof came into picture. Okay, and experiments like in 1927, Davison and Germer, they did one experiment, and of course, they did not intend to show that electrons are behaving like a wave. They wanted to try to study the surface morphology of a nickel material. And in that process, you can say it is accidental experiment. They found that this electron, when they are going to hit the metal surface and they when reflect back, they're going to produce a diffraction pattern. They produce a diffraction pattern. And now they calculated the lambda, okay, from the diffraction pattern, okay, and this lambda was matching from the de Broglie calculation. So the experimental lambda calculated from the diffraction method was matching completely with the de Broglie, okay, for the electron. And that established that these electrons are actually behaving like a wave here. And this way, it was confirmed that electron or matter not only going to have their particle nature, but they also show their wave nature as well. And this is the way the confirmation came into picture. And not only Davison Germer, but even G.P. Thompson, okay, he parallelly did this experiment, specifically focused to prove that electrons are actually behaving like a waves. Okay, so there is a very famous quotations in the scientific community, because the father of the J.P. Thomson, J.J. Thomson, so he invented electron, and he said electron are a particle. And his son, J.P. Thomson, he said electrons are a wave. So this was the interesting quotes were circulated during that time. But anyway, coming back to further into down a little bit. So now we know that electrons, they behave like a wave. So they behave like a particle also, and they behave like a wave also. But the question that how then this wave look like when they behave like a wave? So when you talk about EM wave, so EM wave, in the EM wave I mentioned yesterday also, something is oscillating. And what is oscillating? That is the electric field. It's a physical quantity which you can measure. But when the electron behave like a wave, what is oscillating? No one knows. Even today also we don't know. So after trying for many decades, when the scientists scratched their mind completely and didn't find the physical interpretation, okay, of the wave, then they focused on the mathematical mathematical form of the waves. So they tried to find the mathematical equation of the waves, and in this way they said if electron, let us say, or any charged particle or any particle is a free particle, okay, they with some strong arguments, they found that these when these electrons are going to behave like a wave, then this wave is going to actually look like a wave packet, but not in a real space. Be careful. We don't know exactly what is oscillating in this. So this is not a real wave. Don't think that something is oscillating. You can't say. It is only a mathematical expression to show the wave. The mathematically, it should be like a wave packet, but never try to make any argument like saying that something is oscillating, some physical quantity is oscillating. There's no physical quantity is oscillating in the wave as up till right now, what our understanding we have. Now, further, mathematically, if you further look now into this, then we also know that this kind of waves are actually formed by superposition of a large number of monochromatic waves of a fixed. Monochromatic means lambda is fixed. Let us say lambda 1 here and the lambda 2 here. And particularly here, I can call this wave as a phi 1, this wave as a phi 2. And this phi 1, of course, you can write down. Okay, this is going to be a some amplitude A time iota k1 x minus omega t, like that. Or you can say A time e power iota p x minus e t upon h cut. In the momentum form, you can say P1 here. Or maybe I can just ignore the time part, not required here. Simply I can like this way. The phi 2 similarly, or P1 here, nothing but h upon lambda 1. Similarly, phi 2 you can write like e power iota P2 x upon h cut. Similarly, so on. So you can see that mathematics gives us the evidence that this wave packet is nothing but a superposition of phi 1, phi 2, and phi 3. So mathematically, I can write the psi 1 as actually a like this way. And this indicates that the wave function is actually superposition of a large number of such waves. This is true for a discrete. This is true for a discrete waves, And once you try to look into for a continuous wave, for example, this is the continuous, then for continuous, the same thing, I mean, the psi can be treated like a integration of some wave like phi p and dp. This is for continuous, this is for discrete. I mean, discrete system, then I can write like a psi x equal to summation of ci and phi ix. So this is for a discrete system, and this is for a continuous system. So this gives you a strong evidence that the wave function, okay, whose physical meaning is not known to us, but mathematically this wave function is written as a linear combination of a large number of such monochromatic waves. Okay, and these monochromatic waves, I explained you in the last class also. For example, think about the case of finding the momentum, okay, of a particle. So if you want to find momentum of a particle, then in the quantum mechanics, what we do, we're going to operate this on the wave function. And you will see that in principle, this particle has a momentum spread. So this particle going to have a momentum spread continuously from, let us say, P1 to P2 or P to some P plus dP. And when you do the measurement, then you must get a single value, a single momentum value. So let us say the momentum value you get is the P2. It means that simply this is a correspond to P2 and this correspond to P3, this correspond to P1. So this simply indicates that after the measurement, when you get this value, then these informations are lost. Means only this wave function will survive, and then P going to operate on this. And you know this P written like a minus iota h cut del by del x. And you see here, this phi 2, nothing but e power iota p1 x upon h cut. And this tells you that this is going to be a p1 into phi 2. So this also, now in the quantum mechanics, we say that the phi 2 is a eigenvalue of momentum p. And sorry, P2. P2 is eigenvalue, and phi 2 is eigenstate operator P. Similarly, you can see phi 1, phi 2, phi 3, they all are eigenstate. So we can come to conclusion that operator P has many eigenstates, phi 1, phi 2, phi 3, and so on.
Sir, eigenvalue is P1 na?
Yes,
Not
eigenvalue is
P1.
in this case, for the case of phi 2, it will be a P2.
But it is written a P1
Yes,
psi 2.
sorry, this will be a P2.
No, eigenvalue is P2 because we have
Yes.
taken the second term.
Exactly, it will be P2. So this also indicates that operator, which is we call as the observable, they have a set of eigenstates. So these are called the eigenstates. And from here, in the quantum mechanics, you get a very important conclusion. If you know all set of eigenstates of any observable.
Sir,
Yes.
sir. Meanwhile, while you are okay presenting the topic, okay, some network issues are happening, sir. So, okay, kindly try to share the videos also, sir. Actually, we are following, but meanwhile, some topics, okay, some continuation we are missing, sir. If there is any such a disturbance happens,
No
okay,
problem.
please. Yesterday also same I have mentioned in message also, sir. So topics are very much interesting, sir. But due to some problems in network, so we are unable to connect the topics, sir. So
I will discuss. I will discuss with Sunil, and let him. I will ask him how to now provide this video to you.
Okay, thank you, sir. Thank you so much.
So we will provide you today only. So another very important now conclusion of the quantum mechanics comes into picture here is that if you know the all eigenstates of an operator or observable, okay, then any wave function, any arbitrary wave function can be written as a linear combination of these eigenstates. Already we have written here. See, the psi x written as a linear combination. So this indicates that, and where phi 1, phi 2, phi 3, they all are the eigenstates of a operator P. So this also proves that if you know the complete set of eigenstates of operator, then any arbitrary wave function can be written as a linear combination of these eigenstates. Similarly, if you have operator, let us say some B operator, and corresponding to B operator, you have the, let us say, wave function eigenstates chi1, chi2, and chi3. Then the same wave function, like here, the same wave function can be also written as a linear combination of eigenstate of the operator B. So this is very interesting outcome in the quantum mechanics, that if you know the but must make sure that you must know the complete set of eigenstates. Then any arbitrary wave function. So any arbitrary wave function can be written, the same wave function can be written as a linear combination of the eigenstates operator P, and also as a linear combination of eigenstate operator B. And similarly, if you have a C also, you can do for the C as well. Okay, so this was the first step to explain that how from the de Broglie, if you look carefully now and try to revise what we discussed. So I said that inspired from the Max Planck, which says that the radiations are actually behaving, have a dual nature. It behave like a wave and particle both. It behave like a wave and particle both. De Broglie says that why not matter can have a wave nature. Of course, it behave like a particle in natural form, but why not it can behave like a wave? And then he proposed the idea of the de Broglie wavelength. And this hypothesis was supported by experiment, that is the Davison-Germer and G.P. Thompson. So this experiment finally gave the concrete evidence that yes, electrons, proton, neutron, or any matter is going to behave like a wave. Okay. And since we don't know the actual form of the wave, okay, then we are relying completely on the mathematics. Okay, so instead of looking toward the physical interpretation of the psi, researcher and the scientist, they try to develop the mathematics of the wave function. And this is the reason that in today's also, we always try to say, if you want to understand the quantum mechanics, stick to the mathematics. Don't try to make too much interpretation or physical interpretation. You will going to be disappointed at the end. Because from the starting itself, you can see we don't know the physical interpretation of the wave function. And everything from then onward, it depends only on the mathematics. There is a hardly any interpretation you can draw in the quantum mechanics. And then I try to explain that, for example, for a free electron, okay, with a strong argument, I will share my notes. And in the notes, I have written down the everything. What are the evidences which led to the conclusion that a free particle, a wave function, must be look like a wave packet. The simple argument I can tell you, for example, if you look at the Born interpretation, so the Born interpretation says that the psi square is actually a probability of finding the particle, okay, at a particular location. So if you look at this electron, and if this electron is present, okay, at certain location, then at that location, the probability should be higher. And this probability nothing but a psi square. It means the psi must have a higher amplitude at the vicinity where the electron is present. But as you go away from the vicinity of the electron site, then the probability of the electron to find there will be negligible. And it indicates that the wave function, the amplitude of the wave function must go down, because that square gives you the probability. So this indicates that the wave function must have this nature, which will look like a wave packet. And so this was the evidence. Evidence came from the conclusion, some observations. And then this mathematics of the wave packet, already we know that wave packet are nothing but a superposition of a large number of monochromatic waves, okay? And these monochromatic waves I can represent having a concrete wavelength, fixed wavelength, lambda 1, lambda 2, lambda 3, and so on. And corresponding the wave, I can write like a phi 1, phi 2, and indirectly I can say this whole wave function of the wave packet is written like a superposition of this individual monochromatic wave, which are called phi 1, phi 2, phi 3. And in this way, you can see that the wave function is written in this format. And I have just proved also that this phi 1, phi 2, and phi 3, they are nothing but the eigenstate of the momentum operator. And this also tells us that if we know the complete eigenstates of a operator, let's call momentum here, then any arbitrary wave function psi can be written as a linear combination of the eigenstates of that particular operator. And from here, we also get another evidence, the argument that if we have another operator observable, and if you know the complete eigenstates of that operator, with the same argument, I can say the same operator or same arbitrary wave function can be also written as a linear combination of eigenstate of the operator or observable B. Clear to everybody? Anybody want to ask any question up till here?
So is there a reason in quantum mechanics why we often deal with, why we often start with a free particle, not with any random case? Is there any reason behind that?
I mean, so at the starting point, okay, it was much easier to develop some intuition of a wave function, okay, of a free particle, okay. It was much easier, but after development of the Schrodinger wave equation, we know almost the wave function of majority of the systems. So it is if you think about if you are a person who want to develop some intuition about the wave function, and wave function are not in existence, okay, so the simplest system for you is the free particle, okay, because you can think, you can make some kind of intuition that if there is a particle here, let's say electron, then how its wave function should look like. Not wave function, but I can say how the probability will look like, probability of finding. So I can say the probability, if I draw the probability here, so the location where the particle is present, the probability should be maximum. And when you go away, this probability must go down, correct? So this probability must have this kind of this kind of behavior in this case. And this probability from the look at the Born interpretation, nothing but a psi square. So this indicates how the wave function should look like. Then look at the envelope of the probability, and then this wave function must going to have this nature. So this is become much easier for any person who is starting to develop some theory. Okay, he needs some kind of intuition, and the free particle gives that liberty to make such intuition.
Thank you, sir.
Clear up till here now? Okay, good then. Further moves then. Now I will now focus on the discrete system. Discrete system means a system in which the eigenstates are limited. Okay. You can say n number of eigenstates, but they are limited. Okay. So for example, think in a case of a spin. So in the case of spin, there are only two eigenstates, which we'll show by the 0 and 1. So there are only two eigenstates. When you think about a particle in a box, infinitely high potential box, okay, so there are states which I can show as a maybe a phi 1 and phi 2 and phi 3 and phi 3, and this phi n x is represented, let us say 0 to L. then this is shown by a 2 by L into sine n pi by Lx. So you have n number of states, but they are discrete. Okay. So when you have a eigenstates are limited and discrete. Okay. But not continuous. When you say particle, free particle, so in the case of free particle, although I have drawn here some discrete phi1, phi2, but this is not true. In reality, when you take a free particle, okay, so the number of wavelength, okay, so wavelength will vary continuously. Okay. And for this kind of system, the wave function is written in this format. This is the real format for the continuous system. But just to make a better understanding, I written discrete way, but this is for a discrete system, not for a continuous system. This clarity you must also have in your mind. So here I will focus now, only on the discrete system, whether this is a spin or a particle in a box, or maybe harmonic oscillator, also going to provide a discrete. So for a discrete system, then even for this also, let's say you have a particle here, the particle is trapped in the potential box, infinite potential box. Then if you know the wave function of this electron, let's say psi, so this wave function can be written as a C1 and phi1 and C2 and phi2 and C3 and phi3. Now, if you look at particularly this wave function, particle in a box, in our case here, which I have mentioned. So, and further, you try to look in the Euclidean space, I mentioned yesterday also. And you try to represent a vector R. Then this vector R written like some X into I plus Y into J in 2 dimension. And you can see this I and J, they are called the basis vectors. And you can see that I and dot J, okay, if you look at the dot product of this quantity is going to be 0. Means I and J are orthogonal to each other. And I can tell you that you have a phi1 that is a root 2 by L into sine pi by Lx, and then phi2 root 2 by L sine 2 pi by L into x. Now, in when you talk about functions, so for a function, the phi1 dot phi2, actually it is the integration into dx in all space. And when you calculate, of course, here when you talk about all space, only from 0 to L only. So phi1 star and the phi2 into dx. When you calculate, this comes out to be 0. You can check. It means that phi1 and phi2, they are orthogonal. So this also indicates that when you write down a wave function, a psi like C1 phi1 and C2 phi2 and so on, and in 3D, let us say that are written like x I cap, y j cap, and z k cap, and here let's say C3 phi3 and so on. So here this I, j, and k, they are the basis vector, and they are orthogonal to each other. Similarly, phi1, phi2, and phi3, they are also orthogonals, and this is the similarity you have here between this vector and this. Okay, so the way we say that they are the basis vectors, with the same argument here also I can say phi1, phi2, phi3 are basis vectors. Here, these basis vectors lie in 3D Euclidean space. And you can see that these X, Y, and Z, they are real number. So this space is a real space. This space is a real space. Whereas here, the C1, C2, C3 are going to be a complex. So I will say that these are phi 1, phi 2 are basis vector, but they lie in a complex space, not real space. They lie in a complex space. But here, for example, this is a 3-dimensional space. This is a 2-dimensional space. And here you can have a large number of such vectors. So I can say the dimension here, the dimension can be n, okay? Is a complex space of n dimension. And this complex space got a very special name, and that is called a Hilbert space. So like Euclidean space, that is a vector space, is a real space. Similarly, our wave functions, they are orthogonals. So they behave like a basis vector, the way behave they're not thinking about IJK. So we can call them as a basis vectors. But they are complex quantities. C1, C2 are complex quantities. So we can say that these basis vectors, okay, or these vectors, they lie in a complex space of a dimension n, and this complex space is what is known as the Hilbert space. It is similar like a Euclidean space, but Euclidean space is a real space and Hilbert space is a complex space. In the Euclidean space, I, J, and K, and any combination of I, J, K, they lie in the Euclidean space. Similarly, in the Hilbert space, this phi 1, phi 2, phi 3, and so on, they all lie in the Hilbert space, and not only phi 1, phi 2, but psi, or maybe another wave function chi, okay, which is written as a combination of phi, they all lie in the Hilbert space. So Hilbert space is of n dimension, okay? So the n minimum is 2, and that is for a spin. So minimum is 2, okay? Maximum can be anything. And max can be anything. Anything you can imagine, okay? So this is the way you can understand the Hilbert space concept, okay? And of course, later on Dirac, he proposed that instead of dealing in the wave function term, we can also represent this in the ket notation or Bra notation. So we can write it like a phi 1 and a phi 2 and so on. And similarly, I can also write like a Ci and phi I. So this is just a Dirac notation in the ket and Bra. It gives more flexibility in the algebra of quantum mechanics. So please let me know if anybody having any question up till now. So I think we have done this basic parts, and now after this I can come to our next topic, that is called where we're going to focus, that is called spin. Because whole complete quantum computation I'm going to explain by taking spin as a qubit. So I will try to spend next 1 hour completely on the spin. Okay, so before I proceed to the next topic called spin, if anybody having any doubt, any question, please discuss.
Good evening, sir.
Yes.
Sir, C1, C2, and C3, etc. is a complex number.
Yeah.
And phi 1, phi 2 are complex number. Both are complex.
Yes, definitely. Yeah.
Then
Functional form of is there. This is going to be complex number. Yes.
okay, then two complex joint are wave function in our quantum mechanics.
This is a function, remember, and this is a number.
Okay, sir.
Okay.
Okay.
This is scalar quantity, right?
Means C1, C2 are
Ci are
complex.
they are a scalar. Okay, they are complex
Okay,
but scalar, correct?
Okay, okay, scalar.
And all
Right.
phi I are functions, correct?
Example that x plus iy is a function and scalar 1, 2, 3.
Exactly,
Like that. Yes.
2
Thank-
plus 3i like that, okay?
Okay, sir. Thank you, sir.
Okay. Another thing I will like to mention before I go to spin, called measurement. Measurement in quantum mechanics. I will take the same example. Think about a particle in a box.
सर आपकी आवाज नहीं आ रही.
Yeah, I think there is some problem with Sugam's audio.
Okay,
Yeah,
now
he's
I'm audible.
Yeah, now you are audible.
Yes, thank you. So there was some network issue, and because of that, I was disconnected. Okay. So I was discussing. I'm audible to everyone?
Yes.
Yes, sir.
Thank you. So I was discussing about the measurement in quantum mechanics. So this is a particle, okay, which is in the potential box, and the wave function of this particle, okay, written like a Ci and phi ix, or you can say a C1 phi 1 plus C2 phi 2 and so on. Now see, if you want to do some measurement, let us say you want to measure the energy of this particle, okay? Then what I will do in the quantum mechanics, we have to operate the corresponding operator on the wave function. So when you're going to operate h, let us say on the wave function, okay, then for example here, think about, let me take you back in this part. So when we shown that this particle, a free particle, has a wave packet shape, and the momentum has a spread. And if you try to, and the wave function of the particle written in this format, and when you try to measure momentum, then what will happen? The wave function, only one value you will get. Either you can get P2, or you can get P1, or you get P3, or any continuous value in between you can get. It means other informations are lost. Other wave function are disappeared after the measurement. This is what is called the collapse of the wave function. Similarly, if you try to measure position of the particle, so in the case of position, then you can see that this particle, so you see that this is how the wave function look like. And I can say this particle is present between x1 to x2 everywhere. And when you do the measurement, let us say if I do a measurement x on the wave function psi x, okay, then maybe the particle is going to be located here. at this position. Maybe I can call x0. So what you will get, I mean, then want to operate x on the psi x, then you have to write down the psi x as a linear combination of the eigenvalues of the x. And those are nothing but a delta functions. And you can see that you're going to have a, let us say, x naught and delta x minus x naught. So that is the state you're going to get at the end. Maybe if you, so other information of the position is gone completely. So you can see that in that situation, this delta x in the discrete scenario, I can say the psi is written like a ci into delta I, okay, into x minus xi. So this is how I can represent the wave function as a linear combination of the eigenstates. They are the eigenstate of the operator x. And when you're going to operate x, then only one value will survive, other will be gone. So this is called the collapse of the wave function. Maybe next time you do the measurement, so next time the possibility that you may get the particle here, let us say position x01. So in that situation, when you're going to have x into psi x, you're going to have then x01 and then delta x minus x01, like that. So that is what is called the collapse of the wave function. This is what I'm trying to emphasize here. When you're going to operate h, okay, on the side, then the wave function going to collapse. So you will, this wave function going to collapse either in phi1 or in phi2 or in phi3. So if the wave function collapse in the phi1, then only phi1 will left, other wave function will collapse. It means this h is going to operate only on the phi1. Okay. And the corresponding energy, let's say energy is here E1, then you will get E1 and the phi1. If the wave function collapse to this, then h operate on the phi2, energy for this state is E2, then you will get E2 into the phi2 and so on. So either, remember, in one single measurement, you will get either this value or this value or this value. Only one value you will get, remember. So for example, again, I'm going back and let me explain a little bit because this is very important in the quantum mechanics. So for example, you want to know exactly what is the position of the particle. So maybe when you do the first measurement, it's possible that the particle may be here in the first measurement. In the second measurement, maybe you can get the particle here. But for second measurement, then you need a wave function, a different wave function. It means that if you want to do large number, if you want to actually find where the particle is, then what you have to do? You have to create large number of such wave functions, identical wave functions. So you have to create, for example, there's one particle, another particle, another particle. So you have to create identical wave function. Wave functions, and then find the position. Maybe you will get position here, x01, x02, x0, and x01. So this is how you can get the positions value. Okay. So you have one electron, second, third, fourth, and so on. So you take n number of electrons, identical electrons, and
I think there is also one more disruption. Please wait.
yes, there's a disruption I can see because of network issue at my end, actually.
Yeah. Okay. Yeah.
So can you let me know where I was before my network gone bad? Did
It
you
was very
heard
short.
about this one? When I was
Yes,
saying
sir.
that, okay. So I was
Can
saying
you,
that,
excuse
yes,
me, can you please explain that again?
see,
The one
what
that
I'm
you're
trying to
showing.
say here is that I will come back to this part again. What I'm trying to say here, if there is a particle and this particle is behave like a wave, and if you try to measure the position, so in a single measurement, you will get some position. You will say the particle is somewhere here. But technically, if you look at the probability here of this particle here is less. So if you really want to get what is the exact position of the particle, so what you need to do? You need to do large number of measurements. And remember, after each measurement, the wave function is collapse. So this wave function no longer remains in existence. So once the wave function collapse, you are nothing, you are this, you don't have anything to measure again. So this gives the value, let us say x01. But I want to measure the position of the particle. Then what I will do, I will create large number of electrons and I will prepare electrons in the same quantum state. Okay, so that each and every particle have the same wave function. So I'm going, the term we use ensemble of identical particles prepared in the same state. So that is called the ensemble of the identical particles prepared in the same. So do have so many large number of particles and they have the same wave function. And now you do the measurement. So this wave function and do the measurement at the same time. Okay. So the X operates on each wave function at the same time. And at the same time, because if time is not the same, then remember this wave function also evolve. So if you do the measurement here at, let's say T1, and on the next particle at time T2, then maybe the wave function may evolve of second particle. So that's why it's important that you do the measurement at the same time. And after this, you will get all the position values. And let's say you have n number of particles and you have n number of position values. What you do, you get this position value, let's say 0, 1 and x02 to so on, and then divide with this. Okay. So you get the average position value. And this is what is called the expectation value in quantum mechanics. So remember, in the quantum mechanics, it is a very similar like average value in classical system. Think about that. Let us say if you want to measure the time period of pendulum, what you will do? Okay, you take a stopwatch, and then let this pendulum oscillate for later 10 oscillations, and then you take the time and divide by 10. Okay, so you will get one value. So let us say t here, you get, let us say 2 seconds, but it's a one value. Okay, so if you want to exactly get the real number of time period, what you will do? You will repeat this measurement at many times, correct? Maybe next time you will get 2.1, 2.2, 1.9 like that. Okay, and what you do then? The t average you take. So t1 plus so on plus. This is how you do actual measurement in the classical system. You take a pendulum, then do the measurement of time period and time, okay, and then take the average value. But advantage in the quantum classical system that the system on which you measuring the time period remain the same. Means you do the measurement at time t1, at time t2, at time t3, the length of the pendulum is never going to change. The pendulum remain the same. But in the quantum system, the problem is that once you do a measurement of this wave function, so once you apply the wave function on the wave, x on this wave function will collapse. This wave function no longer remains in existence. It's like if this pendulum, just imagine, if this pendulum is a quantum pendulum, and then you do a measurement of the time period. After one measurement, this pendulum no longer remains the same. Maybe its length will change, let us say. Now, if the length changes and becomes, let us say, longer, so this is a new system. So on the new system, you can't do the measurement to get the value of the earlier pendulum. This is a new pendulum. Okay, this is what I'm telling. In the quantum mechanics, you have a wave function. Once you do the measurement, the wave function will change. That's why you have to create identical wave functions. For that one, you need identical particles in the same quantum state, and then do the measurement on each particle at the same time. Then you will get the position value, and this position value you can add and take the average, and that average is what is known as the expectation value. Is this clear to everybody? What is the mean by the expectation value?
Yes, sir. Sir, can I ask one question?
Yep.
Sir, as we know, the operator play two roles. If we operate on some system, some wave function, it provide corresponding average value that is called basically eigenvalue. And other role of
Average,
operator.
not a single, single measurement. You have to do large
Yes,
number of
sir,
measurements.
yes, sir.
Yes.
So
Yes.
all those will give average value, that is
That's
expectation
true.
value. Yes, sir. And other role of operator, as mentioned, that it is playing or acting like a state changer. Means when we apply some operator on any wave function or any state, then state also change. So whether
Actually, your
it is
voice is breaking. I think the same problem to everybody. Other people can hear him completely, or
no,
is problem at my end only?
sir, can I repeat? I am saying, sir, the operator play two role. One role is I have already mentioned. Second, when we apply some operator on some state, it change the state. So
Say again, please.
it change the state changer. Operator also usually expressed or mentioned as it act like a state changer. So what
Yes,
it
that's true.
means when you are saying the state collapse. So in that sense, they say the state operator act like a state changer.
Yes, I mean, so when you talk about observables, then in that
Yes,
situation
sir.
we talk about wave function collapse. But you talk about normal operators, okay? So, for
Yes,
example, if you have any operator, no, called, let us say,
yes, sir.
1, 0,
Momentum. Yes,
2,
sir.
1, like that. If you operate on, let us say, 1, 1, okay?
Yes, sir.
You can see that this is going to become 1 and this is
Mhm.
going to become 3. So this is
Mhm.
the operator A and this is a state, correct?
Yes, sir.
And now this is become state Y. So this is the reason we
Yes, sir.
say this is state changer.
Yeah, but I want to know in physical sense, sir, as you told, uh, as you discussed regarding the position we were measuring. So
Mhm.
in physical sense, what is the meaning when we say state change? Whether it is similar to that of collapse of wave function or what? That
Yes,
is the
it is similar.
confusion.
Yes, exactly. Yeah, yeah.
Yes, sir.
That's
Thank you.
true. I
Thank you,
mean,
sir.
this is true also, no? Look at it.
That was confusion, sir, only.
This internet is getting crazy here today. Yeah, exactly. Similar. For example, when you say there is a wave function written like a And when you operate operator on the psi, you finally going to get something, some value, let us say A into phi 2. So earlier you had a psi, now you have a phi 2.
Okay. Sir, we are not able to see the screen board.
Maybe your screen setting is turned off.
Okay, so let's move forward then. So I was telling you the measurement. So we have a wave function psi written like a C1 and phi 1 plus C2 and phi 2 plus C3 and phi 3 and so on. And I told that you can think these eigenstates like states of a particle in a box, phi 1, phi 2, phi 3, energy E1, E2, and E3. And when you're going to operate H on the psi, the wave function, then either you're going to get phi 1 or you're going to get phi 2 or you're going to get phi 3. And in that case, H will operate on this and you will get energy E1 and phi 1. And here then H operate here, then you will get energy E2 and phi 2. Now, the interesting part here, what is the probability of getting energy E1?
May I ask a question?
Yes.
Yeah, so this is Aman. So let's say if we prepare, this is true when you have a system in a general state, let's say psi. But what if we prepare a system in any of the eigen state of phi 1, phi 2, phi 3, then will this
Then no,
measurement problem will appear?
No, then there is no collapse of the system. Yes.
Yes, that was my question. So let's
Yes.
say so we can avoid the measurement problem if let's say, I mean, every time if we prepare a system in a known state in any of the
But you cannot do that. That is the problem.
but yeah, as that was my next question, that is it always possible that we can prepare a system in
No, you cannot. This is the problem. You can't prepare the system in the one particular state. That is against the Heisenberg uncertainty principle. If I want to say, okay, the particle always remains in the phi 1, this is not possible.
but theoretically we can do that. Let's say that I mean
Even
we have,
theoretically also you can't do it, okay, because this is the violation of the Heisenberg uncertainty principle. So if a particle is in the particular state, it means the energy is defined, correct? Because each quantum state has a fixed energy E1, and when you prepare a particle in this system, it means its energy is known to you. Momentum is precisely known to you, okay? And momentum is known, then it is a violation of the uncertainty principle. This is what uncertainty principle says, that delta X and delta P cannot be measured, okay, with the 100% accuracy. So you cannot prepare a particle in the eigenstates. Practically not possible. Theoretically also not possible. This is a violation of the Heisenberg uncertainty principle. So whenever you say there is a particle, okay, then you should not say that the particle in this particular eigenstate. You always say the particle has a wave function. It might have the probability to be in the phi 1, okay, very high probability. It can be 99% probability to be here, but still you have to say that the psi is a combination of a phi 1, phi 2, and phi 3. Maybe when you're going to calculate, okay, that what is the probability that the particle is in this state, okay, and that probability you can calculate, and that probability will be equal to C1 square and divide by summation of Ci square. So the square of this quantity will tell you that what is the probability that the particle will be in this state phi 1. Okay, this probability may be 99.9%, Okay, but still you cannot make it 100%. It is
So that okay. So you mean to say that, I mean, measurement problem will be is an intrinsic problem of
exactly.
in the
Yes,
quantum system. You
definitely.
cannot avoid it in any case, right?
In any case, yes.
So okay, fine. But this is not true for the classical system. They have a definite
Not
system,
definitely.
and
Yes.
here, because of the because of the, I mean, the nature of the quantum system, we cannot
Yes,
avoid.
you cannot avoid. That's true.
Okay, thank you.
So you can see that you can when you do the measurement, of course, to do this measurement again, you will repeat the measurement many times. Okay, and then only you can tell what is the probability of the particle to be in the state E1. Okay, and similarly you can find what is the probability of the particle to be in the states C2. That is from this formula. So please write down. There can be some questions based upon these simple mathematics which we are discussing. So this is a measurement problem. Okay, so whenever you do the measurement, the wave function going to collapse. Okay, so that's all for the fundamental part. And now I think we are ready to jump into the spin and Stone Gerlach experiment. And this is the portion where I mentioned that I will like to spend most of my time. Okay, so further, any question before that before we start this topic?
Yeah, so if you want to understand how the ensemble average is different from the classical average, is there any easy way to understand?
The quantum average, okay. When you say quantum average means expectation value, correct?
Mm-hmm.
So they are different. They are completely different. They are different from the point of view of the measurement. So in the classical system, when you take the average value, you take the average value on the same system at a different time. So you do the measurement at different time. Okay, and then take the values and take average, correct?
Mm-hmm.
In the case of pendulum, for example, you take the average value of the time period, let us say at time t1, and that you note down. Then again you swing the pendulum and then again take the value, again take the value. So you take all these values at different time and then take the average. Okay, but in the quantum system, because of this collapse of the wave function, if you prepare one wave function, that's not enough, because after the wave function, after the measurement, this will collapse. So this for this one, then you have to prepare n number of particles and you have to prepare them in the same quantum state, and then you have to do the measurement on each particle, okay, at the same time. So only up till this point, okay, the classical and the quantum are different. After this, you get the values of x1, x2, x3, and x3, and the next, the numbers, average value, okay, mathematical expression remain the same.
Sir.
Okay, the mathematical expression remain the same, but you must understand the measurement procedure in both the cases. So in the classical system, you measure the value on the same system at different time. In the quantum system, you prepare large number of such particles and in the same quantum state and do the measurement on each particle at the same time. Is equivalent to like saying that I have a large number of pendulum, okay, and then swing all the pendulum at the same time and then get the value T1, T2, T3, and T4, and then take the average. I hope now it makes sense to you.
Yeah, it seems like a time average over here. Okay.
Not time
Whatever.
average,
I
it is
mean,
still a number average, but you
number
taking
average.
but these values you're taking a different time.
Different
Okay.
time.
Yeah. On the same system. But here you're taking these values x1, x2, x3 on different wave function. Of course, they're not different, but they are different.
Identical wave functions.
Exactly,
And
identical wave function.
okay, thank you.
Sir.
Mm-hmm.
how are we making this
Identical.
identical particles in same quantum state?
Okay. For example, let's say in our lab, actually, we are working on the penning trap. Or maybe Sunil sir also, he's preparing the Paul trap. So the Paul trap is, let us say simply, is penning trap is like three, let us say cylinders, hollow cylinders. And if I put a positive potential here and 0 and positive potential here, then I can create a potential well here, correct? And I can put a particle here, maybe let us say proton. And if the proton kinetic energy is less than the potential height, then this particle will be trapped. So this is in the harmonic oscillator. And I can cool down and I can make sure that the particle higher probability to be in the ground state. I mean, I'm using the word highest probability to be in the ground state. So what I can do, so similarly, this kind of system, I can prepare large number of such system. And let us say I can cool down every system to 10 millikelvin. That will ensure me that each and every particle will be most probably in the nearest most probably in the ground state. So they will be in the same wave function. Are you getting? So I have to create, I have to make physically n number of penning trap, such potential well, and I have to put particles in each trap and cool down to 10 millikelvin. Okay. So I will ensure that all the particles will be in the same quantum states. So this is how experimentally you can prepare ensemble of n particles, identical particles in the same quantum state.
Okay, sir.
And then you can shine photons on each to measure the some values. Okay. So you shine photon on each particle at the same time.
Sir, I have a doubt on this trap.
Mm-hmm.
May?
Mm-hmm.
Okay, so like because of the potential difference, like proton will get some amount of internal energy due to that. So is it not possible that it will move towards negative? And as well, we are also targeting the photon towards proton. So it will also get the internal energy from that photon. So it will also move towards the negative potential. Is it not possible?
I mean, after the measurement, it will disturb, but you got the measurement, and this is what you call wave function collapse, right? So once you get the value, after that, what is doing doesn't matter to you.
Okay, got it. Thank you.
So by the way, how do you decide that this n number of identical system would be sufficient to give me the desired quantity up to certain precision? I mean, this n, I mean, how do you decide that n?
For
We have to
example, let us say,
yeah.
for example, let us say you want to measure spin of the particle, correct?
Yes.
Because there are only two values, correct?
Mm-hmm.
Then for two values you have to measure. Okay, so if I create, let us say 20 states, okay,
Mm-hmm.
then if I prepare the electrons in the spin states, and let us say all are in the ground state, I mean it's on probability basis, then this and do the measurement on each by shining photons, I will get the values, correct?
Mm-hmm.
So this 20 is more than enough. Maybe one or two even are not in the same state. It doesn't matter, right? Let us say one is flipped.
Okay.
Out of 20, then 2 will be in the up state and the 3 will be in the down, other will be in the down state. So when you get the average value, okay, it will tell you that these particles are in the up states, in the ground state. So for two numbers, or maybe 10 numbers also enough, 10 measurements also enough. Okay.
Mm.
But let us say you measuring something which gives output, let us say 100, correct? Variables.
Mm-hmm.
And then you're doing only 100 measurement is not enough, no?
Then it's not, yeah, at least
Exactly.
1,000 or something. So
exactly, this is how you can get some idea okay, how many measurements you need to do.
so depending upon how large your output is,
Exactly.
you can decide what should be the value of n, right?
Exactly. Yes, that's true.
Okay, good. Thank you.
Okay, so now let's come to the spin and Stern Gerlach experiment. So when you talk about spin, so this is a very interesting and very fundamental topic in the quantum mechanics. If you maybe I can tell you a little bit history of the spin, how it came into picture. So even I will share my notes today also. So I tried to write down these history so that when you go through this history of the spin, then it may trigger some more idea, okay, and it can trigger your interest in the quantum mechanics as well. And again, I will request you not to write anything on the board. Maybe you can, whoever written, please remove this now, because this will remain throughout. I cannot remove it.
Yeah, kindly remove the markings which is done on the board.
So see, in the early 1920s, okay, there were now I talk about now atomic spectra. You can think about spectra like a fine spectrum of a hydrogen atom. You can think about anomalous. G-Man effect. So when you talk about a fine spectrum of hydrogen atom, so technically this is think about the situation of n equal to 3 and n equal to 2. And there you're going to have two states. If you consider only the L, okay. So this L is 1 and L is 0. And here, if you only consider L, then there are going to be three states, no? L equal to 2, 1, and 0. And based upon that, if you look at the delta L equal to plus minus 1 selection rules, and if you try to make possible transitions, so L0 to from ground state, on ground state, one transition, this one, another will be this one, and here it will be 0 and 1, and here it will be from 1, and then from 2. So you can see there are only 4 lines, correct? But and this is the transition which is called as the H alpha line. But when you resolve this H alpha line experimentally, using the diffraction grating, what you find that this H alpha line is consist of not 4 but 7 lines. So there are total 7 fine lines. So just by considering the angular momentum of electron, okay, theoretically you get only 4 lines, but experiment says that there are 7 lines in the H alpha, and this was again a bigger crisis at that time. People were not able to understand how to explain these 7 lines. Same thing in the anomalous Zeeman effect. When you talk about a sodium, D1 and sodium D2 line, so D1 give 4 lines and D2 gives 6 lines. And you can't explain total 10 lines just by considering the orbital angular momentum. So these two were the, I can say, just for example, I'm telling you, created one kind of crisis at that time in the scientific mind to think about some other possibility to explain these concepts. And to explain this concept, the first person in 1925, Cronin, No? In solid state, you study about the Croning panning model. So this scientist Croning in 1925, and when you go to history, he was listening to Niels Bohr about the hydrogen spectrum, and from there, when he's heard about this problem in this fine lines, then quickly, he got the idea that what if we can assign another angular momentum to electron, and that has a value 1/2 quantum number. So he said that if we assign a quantum number 1/2, okay, to another angular momentum, you already have a L, and this is called, let us say, S, and if you have L plus S, okay, then these states you can see here, these states depending upon the L value, so L is 2, and 2 plus minus 1/2, this is going to be then 5/2 and 3/2. This is going to have a 2 states then. So he said that we can split the states based upon the another quantum number S. And similarly here also you can split. And then these transitions, when you take into consideration, taking into this is called J, then he was able to explain the 7 lines. So he said that why not to assign electron and another angular momentum, and he called that as the spin angular momentum. Remember that Croning at that time in 1925, he just finished his PhD, and he was in touch with the Wolfgang Pauli. Then he went to meet Wolfgang Pauli in Hamburg, in Germany. And there he explained his idea that if I assign an electron an additional quantum number along with the orbital angular momentum, that is called the spin angular momentum, then I'm able to explain these 7 lines. Then Wolfgang Pauli said, what is the meaning of this spin? Then he said, electron, Bohr model says that the electron has this nature where it's orbiting about the nucleus, but in a stable orbit. And because of this has an angular momentum L. Then the Croning said, what if I consider this electron also has a spin motion? It means it is spinning about its nucleus, about its own axis. Then Pauli said, Pauli has used very harsh word to Croning. In fact, he said it's nonsense. He said very strictly that a spinning electron is a point particle. No? And he gave the argument, if you imagine electron is spinning about its own axis, and nobody know what is size of electron here. Okay, so he said that this is like, let's imagine like a spherical ball. And if you imagine it like a spherical ball, then and it is going to have an angular momentum, let us say S. Then this S will be equal to I time omega. Omega is angular frequency. And this I will be equal to 2/5 time m time r square. That is r of the radius. So he said that from there, and this omega is nothing but a v by r. Let's say this is the moving with the velocity v. Now it's yourself, you can calculate. Now see, this S magnitude will be what? This is going to be S plus 1 h cut, means √3/2 h cut if you take the value of S equal to 1/2 according to the Croning. And he said, if you try to calculate what is the velocity of this rotation, so you can calculate now from here. Look at there, it's the √3/2 h cut, and this I will be equal to just ignore this 2/5. This is equal to mr square into omega, means v by r is cancel out. So there, this V, from there the V becomes what? Root 3 by 2 h cut and divide by what? Divide by mr. So this is velocity. And now if you take h cut equal to 1.05 10 to the power minus 34 joule second, mass of electron 9.1 10 to the power minus 31. Radius, he said, we don't know, but let us take around 10 to the power minus 17 meter, less than the nucleus size. Okay, so can you calculate what is the velocity? Can somebody calculate? Can you put this value there? Just ignore this factor. Just only take these values and try to calculate what is the factor you getting. 10 to the power minus 34 there, and 10 to the power minus 30 here, and 10 to the power minus 17 there. What is the value? 10 to the power 13, correct? Meter per second. Are you getting this value approximately?
Yes. Yes.
So this V is more than the velocity of light. So the Pauli, he said, why he said nonsense? He said this concept is completely ridiculous. So when you considering electron is a spinning ball, then in order to produce this much angular momentum, this electron must spin, okay, with the velocity of 10 to the power 13 meter per second, which is a much more than the velocity of the light. This is the violation of the STR. And he said that, okay, even if you assume the velocity V equal to C into 10 to the power 8 meter per second, and then try to calculate the radius of the electron, what should the radius of the electron? Then this is going to be what? H cut upon, let us say, MV. So this is going to be a 10 to the power minus 34 and 10 to the power minus 30 into, and this is 10 to the power 8. What is the radius? 22 and 8, 10 to the power minus 12, correct? Meter. And this is bigger than the size of proton, correct? Or nucleus, which is high, kitna hota hai? 10 to the power minus 15 meter only. So it means if electron is rotating with the maximum velocity, so then in order to produce angular momentum of 3 by 2 h cut, because that is coming when you consider h equal to 1 by 2, then this electron size must be bigger than the size of the nucleus. So that's why he was not in agreement with the Croning. He said your idea, although by putting this number S1 by 2, you are able to explain these 7 lines, but this is beyond any explanation. We cannot justify. So there is no classical justification for such a spin motion. And in this way, Pauli, he said that your idea is not a good idea. So Croning, then he withdrew his idea, and he never published, remember. And just 2 months later, in 1925 itself, just 2 months later, 2 more young students, Ollenbeck and Goldsmith, they were bachelor student, graduate student. They were working under the Ehrenfest. Ehrenfest, the same person who gave the Ehrenfest theorem. So they were working under the Ehrenfest, and they were trying to understand the atomic spectra, the fine spectra of hydrogen atom and Zeeman splitting, anomalous Zeeman splitting. They're trying to understand this one, and they also got the same idea. They said we can explain this behavior if we assign electron another quantum number that is called the spin quantum number. That value should be a s equal to 1 by 2. And corresponding angular momentum then will be a root 3 by 2 h cut. So they gave this idea to Ehrenfest. And Ehrenfest unlike Wolfgang Pauli, he was a very polite person, and he actually very much inspired with this very new idea, despite knowing that this is not matching with the EMT theory, because of this problem that electron speed will be very high or size will be very high. So he said that to these two students, I mean, I will like to quote that word. He said, well, that's a nice idea, though it may be wrong, but you don't have to have a reputation. You don't have a reputation. So you have nothing to lose. So you can publish. So this way, the Goldsmith and Uhlenbeck, they published this paper, and that time paper was published in the Nature. And before giving the paper to the publication, even Ehrenfest, he sent this paper to get the comment. Okay, he sent this paper to Lawrence to get his comment. And by the time Lawrence given his objection, a same objection what was raised by the Wolfgang Pauli, but before he gave his objection, the paper was already communicated in the Nature journal. And after listening the objection of the Lawrence, Uhlenbeck and Goldsmith, they said to Ehrenfest, better that we can withdraw this paper. And there again, Ehrenfest, again, his quote is very famous. He said, you are both young enough to be able to afford a stupidity. And scientific community will forgive you for your stupidity. And this way, he never withdrew their paper. And this way, you can see this paper was published, although with a lots of criticism at that time. But later on, when Paul Dirac, when he theoretically proposed spin, okay, then it was almost acceptable to everybody that spin exists. Despite this problem, spin exists. And Dirac, he called this as the intrinsic property of an electron. I hope you understood the spin history concept. Any question anybody want to ask here?
Sir, can we know the reaction of chronic then? Do we know that?
Yes, he was disheartened completely. And he was supposed to be and natural also. Even
Right.
Wolfgang Pauli also, okay. He later accepted that he was too rude
Okay.
to Croning. Otherwise, this whole discovery of the spin would have been gone to Croning, not to the Uhlenbeck and Goldsmith.
Yes. Actually, it's a state-of-the-art discovery at that time with limited means of calculation as well as experimentation.
Yes. So only we can say that the Croning was unlucky. And the Uhlenbeck and Goldsmith, they were lucky to have a very nice supervisor.
Right.
Can we extend today's class for 10-15 minutes more? Because I want to finish this Tron Garlic also.
Sure, sir.
Okay.
It's very interesting, sir.
Yeah.
Okay. So just give me 2 minutes. Sunil, can I extend this class for?
Yeah, sure. Go ahead.
Okay, so now let us then come to the another experiment, Stone Garlock experiment, because still you can see that whether it is a proposal by the Uhlenbeck or Goudsmit or Dirac, it was still a theoretical proposal. So while solving the relativistic quantum mechanics, Dirac proposed the spin idea, okay, but it was still a theoretical concept. Remember that this Stern-Gala experiment, this was actually performed in 1922 by Stern and Gerlach. There are two scientists. And the original idea of this experiment was to prove space quantization. Means to prove that angular momentum takes discrete value. So that was the original objective of this experiment. And to prove this, they took a specially designed magnet to produce a non-homogeneity in the magnetic field. So you can call this is the North Pole and the South Pole. So this specially designed poles, you can see that because of this pattern of the magnetic field, the magnetic field here is higher and here is less. So this is create a magnetic field inhomogeneity. And then what he did, he created vapor of silver by heating it in an oven, and the silver atoms then came out. And then he used some slits also to collimate it. And at that time, it was considered that atoms like alkali atom or alkaline atoms, they have unpaired electrons in their outermost orbit. And because of this unpaired electron, they possess magnetic moment. And at that time, there was no spin concept. So for them, the magnetic moment is because of orbital angular momentum. I mean, so if you look at from the Bohr theory, classical theory, that this is how electron is revolving around the nucleus. And then this is going to produce L. And because of this electron motion, it is a current which is is there. So the magnetic moment, according to the classical theory, is defined as the current into area. And when you calculate this area and the mu, so this mu finally, when you solve this, I mean, I can avoid this calculation. So this mu L comes out to be minus E by 2m into L vector. So that is the magnetic moment. Okay, I will not call L or S here, but just magnetic moment. And this is L. Because of L, this L mu is produced. So there is a mu L here. So technically, what I can say, this whole system is going to act like a magnet. So North Pole here and South Pole here. You can see the magnetic field lines are going to emerge from this end and going to merge at this end. So this orbital motion of electrons produce magnetic field. As a result, I can see this system is going to act like a bar magnet. So this is a magnet. Okay. So when there is a magnetic moment, means there is a magnetic field. So what they said, that if I take a silver, and silver, if you look at the electronic configuration, is a krypton 4d10 and 5s1. Okay. So remember, although electron is in the s orbit, but at that time, there's no concept of spin. So for the researcher or the community at that time, this electron, unpaired electron, is going to have angular momentum. And because of this, there will be a magnetic moment. So for them, this each silver atom is actually a bar magnet. So each is actually a magnet. And a large number of such magnets are coming out from the oven, and they are passing through this specially designed magnet to produce a inhomogeneity in the magnetic field. And if you look at, because of the inhomogeneity in the field, if you look at the force that going to act, okay, because once this this magnet is inside the magnetic field, so let us say this is a magnet here, and magnetic moment mu, and this is a B magnetic field, then this is going to create a energy, and this energy will be a minus mu dot B. And the direction, let us say, is called Z. So here, the force on the particle, please go through this mathematics of the Stern-Gerlach yourself. I will just quickly go through it. This Fz will be equal to the gradient, or I can, F force will be gradient of the energy, correct? This is how we write the force now. And when you put this U, then this is going to become mu dot B. And when you calculate, then this is going to be a, now see, this mu is going to have three, magnetic field going to have three components, and so is the mu. So this is going to, and now the magnetic field is only on Z direction. Other components will be zero. Then you will only get the Fz, and this Fz will be equal to mu Z and B Z upon del Z. Okay. So you can see that this is the final force acting on the particles. And this mu Z, when you calculate, so this mu Z is going to be minus G into mu B into mj. At that time, it was J, considered like a J. And now you can see that this Fz is going to be then minus G and mu B. Maybe I can simply call M. That is the magnetic quantum numbers. And this is the value of mu Z, and then curly B by curly Z. And based upon this, if you calculate now the force acting on this particle, okay, and then calculate the displacement, so you will find that depending upon the orientation, this particle is going to divide in two parts. So the one going to go here, another going to go here, and this Z you can calculate how much Z will be there. I'm avoiding this calculation because of time here, but you can do these calculations. And finally, this Z, when you calculate, it comes out to be a G into mu B into M into del B by del Z into M time velocity of the particle along X direction, and L and D. So this L is this length and D is this length. So this is the formula you got. So definitely, first of all, this separation, the splitting of these two magnets, depending upon the orientation, it proves that the angular momentum is quantized. So the original objective is fulfilled. And this proves that, yes, angular momentum are quantized. They only carry discrete values. And further, when you can find the Z, how much displacement will be there. Now, the interesting part is that when you find this Z, okay, see, this Z is known to you. You can calculate, I mean, you can measure this value experimentally on the screen. Del B upon del Z, this is a gradient, also known. Everything is known. And from there, you can find the G into M. This is equal to Z time M Vx square upon mu B into del Bz by del Z into L into 2. These terms is known to you. And the interesting thing that this G into M, when they calculated, they got the value plus minus 1. And in 1925, after the discovery of the spin, people found the interpretation of this value. And what they said, ki, this Landes G factor, no, you can calculate, and based upon this Landes G factor, okay, when you look at the M value, okay, this M value comes out to be only plus minus 1/2. So they said that whatever angular momentum we have here, this angular momentum corresponding quantum number is going to be half. And this was matching with the discovery of the Uhlenbeck and Goldsmith. They said that this electron going to have a angular momentum quantum number called 1/2. So after this, the spin was confirmed. So there was, after this, the scientific community, they confirmed that this quantum number actually is not because of the L, because L cannot take 1/2 value at all. Okay. So they said this quantum number is actually correspond to the spin angular momentum. And after this, the spin angular momentum was confirmed experimentally. And then this value √3/2 h cut for electron is also confirmed. So you can see that how this Stern-Gala experiment, not only, of course, this was meant to prove only the space quantization. But after the discovery of the Uhlenbeck and Dirac, people made this interpretation more deeply, and they figure out that this M value comes out to be 1/2 by calculating the G value. Okay, because G is, you can see, this is equivalent to 1 plus, I think, G something something you can figure out. Okay. So from there, this value comes out to be 2, and then M comes out to 1/2, and from there, this value of angular momentum comes out to be a √3/2 h cut. So this way, this experiment, Stern-Gala experiment, play a very important role in the quantum mechanics, because it confirms not only the space quantization, but also confirm the spin. Okay, so it plays a very important role in the quantum mechanics. Now, coming to my second part in the Stern-Gala. So onward now, what I will do, I will represent the Stern-Gerlach whole apparatus as a box. Okay. And so this is a SG experiment. And here is the oven, which produced the atoms having magnetic movement. And let us say if the magnetic field is along the Z direction, then I will say this beam is splitting in two parts. Okay. So first, let us say Z plus, another is a Z negative. This corresponds to, let us say, up spin, and this corresponds to, let us say, down spin. So onward, we're going to represent SG experiment in this way. Clear up till now? Now, quickly I can go to combination of SGs. So let us say you have a oven, and this is going to pass through one magnet, and now I will say Z direction. And there the beam is going to split in two parts. So one is called Z plus, another is called Z negative. And here the operator I've been going to call it the SZ. Okay. And if you block this part and again pass this to another Z, then you will see that you will get only one beam, that is the Z plus. And if you further pass this into another experiment in which the magnetic field is orienting along the x direction, and that means you are doing a SX measurement, then again you will see that you're going to get two values, but now the values correspond to different eigenstates, X negative. I'm just writing it. We will discuss maybe in the next class in detail. And again, when you pass through the, let us say, Z, okay. Again, you're going to get a two values, that is a Z plus and Z negative. Again, to do the measurement. Okay, so you can see that this kind of outputs you're going to get. So, but since now it will take some time, so better that now we can discuss the explanation in the next class. So you try to now think a bit more about this part yourself, and maybe in the next class I will explain you the mathematics of spin. Okay, and then I will discuss the blosphere and also a qubit. So from there, I think it is natural to easily we can understand what is a qubit, okay, and how to do the mathematics of the qubit easily in the quantum mechanics, okay. But this one, I think we will then do in the next class. Tomorrow, okay, that's all from this side. Before I make some announcement, but I think I should take your question first. So if anybody have any doubt or question, please ask. Any question? It is clear to everybody what we discussed?
So there was one question. Can you explain the calculation of M as plus or minus half?
Let me see, what was the question?
Calculation of M as plus or minus half.
Okay. So see here, I mean, so in this expression, look at carefully, then this quantity is known to you. This is something you can measure experimentally. Mass of the silver atoms are known. And if you know the temperature of the oven, then you know that also what is the average velocity of the particles coming out. No, you can take the root mean square velocity, VRMS, also known to you. This is the Bohr magnetron, also known to you. The magnetic field gradient, also known to you. The interaction region, also known to you. The free space, also known to you. So all these parameters are known to you. You can see in this structure that some particle will go in the positive Z and some particle will go in the negative Z. And this is going to be, I mean, so when this is known to you, this is also known to you. Okay. So let us say this value is, if this value is, let's say plus Z1, then this will be a minus Z1. And accordingly, when you're going to put these values there, okay, then this G into Mj corresponding to plus Z1, you get plus 1, and minus Z1, you get a minus 1. So when you calculate this value, you get G into Mj plus 1. Okay. And the only possible combination of G into M, okay, if you look at the Lande G factor, okay, expression, the only possibility of these two numbers is 2 into plus minus 1 by 2. Only this possibility can give you the answer plus minus 1. You cannot have other possibilities. You can calculate, you can try out, you can look at the value of G, what numbers you can have. So G into Mj, only these possibilities, these two, only one possibility can give the value plus minus 1. You cannot have other possibilities. So this indicates that this M is actually equal to plus minus half. That makes sense to you now? Any other question? Yes, Nirbhay Singh, you want to ask any doubt?
Sir. Thank you, sir.
Okay. Okay, so tomorrow, according to schedule, is a break. Actually, I have some involvement tomorrow, but still it is not 100% confirmed. If I'm not going anywhere, then I will like to have a class tomorrow also. Is this fine?
Yes, sir. No problem, sir.
So I will inform you in the WhatsApp group,
Yes.
latest by let us say 4 o'clock in the evening, whether we're going to have a class tomorrow or not. And if we have a class tomorrow, then we will discuss this mathematics of spin and Bloch sphere and qubits concept. All right, then shall we stop here?
Yes, sir.
Okay, I think we can now
Thank you, sir.
stop here.
And I will share my notes today to you. And I think already you have that book, no, PDF file. Somebody already has shared that PDF file to you in the WhatsApp group. Maybe you can again reshare so that the people who join later the group may also have access. And today I will share my today's lecture note. For today's lecture note, you can follow any standard quantum mechanics books. No, generally my notes are from the Sakurai. Okay, but you can follow any other notes also. Doesn't matter.
And sir, the class recordings will be helpful.
Yes.
Sometimes I would like to recall something or what you have said, so they will share the class recording.
Okay. Sunilji, how to do that part?
Yeah, currently it is in the Zoom cloud, and I'll see whether we can directly share it from the cloud, or otherwise we'll have to host it in a YouTube or something. Yeah, we'll check. We will discuss that.
Okay.
Okay.
Another thing, sir, then it will be helpful if you please allow us to record the screen by each of us. I mean, I can send a record request. So if the host approves, then I can record the video of my own.
I think not required. We will share the video to you. Don't worry.
Okay, okay.
We will just figure
Sir,
out.
I think you can, sir, share at YouTube because in previous at time of COVID, there was some link on YouTube also.
Yes, I think
So
we will
that-
provide there. Yes.
Yes, sir.
Yeah.
That's good, sir, for everyone.
Yeah.
Thank you, sir.
Okay, so now I think we will conclude today's session, and yeah, so shall we stop now, Sugam?
Yeah, yeah.
Okay, okay then. Thank you, everyone.
Okay,
Thank
see you
you.
then.
See you.
Thank you.
Want to ask, sir, can I ask last one question?
Mm-hmm.
How I can be member of Indian Society of Atomic Technology?
Sunil sir will tell you.
Because I am a student of material physics, sir, experimental science. I have no paper, nothing in field of atomic and molecular physics or sciences. So I am a student of basically, sir, carbonaceous materials for energy storage, lithium and sodium ion battery. So, but I am interested, sir, just because of your lectures. So, it would be better for me if further I will be connected and getting some uh, updation regarding those things, and I want to learn these things, sir.
So, Sunil?
Okay. Yeah, I think you can send an email to this ISAMP email ID, and
Okay, sir.
then I will reply to that email.
Okay, sir. And sir, one thing, one doubt, not related to Sugam, sir. I am registered with another email ID, but when I join through the institutional ID, so any problem in attendance, or you can consider, because now it is not changing. I am joining through institutional ID.
Okay. Yeah, I mean, maybe you can also mention this in your email.
Okay, sir. Thank you, sir.
Yeah.
Thank you so much, sir.
Thank you. Okay then.
Okay, then. Good night, everybody.
Okay. Okay. Good night. Bye.